All right, so I'm going to try to fit this last chunk of notes in to this 10-minute video. So the last part has to do with the gas laws that exist. So in order for us to talk about gases, we need to make a little comparison to solids and liquids. So if we were to look at particle diagrams, we've got solids that are very tightly locked in place. They still vibrate. And then a liquid is free to slide past each other, but the molecules are still very close together. And then a gas, what's different about a gas is the particles are very, very, very far apart, and they're very free to move around, and so they move all over the place. The shape of a solid is a very definite or rigid shape. For a liquid, it's going to take the shape of the container. For a gas, it's going to fill in any available space. The volume for a solid is also fixed or definite, like we can measure it. For a liquid, same thing, it's fixed or definite. You can pour it into like a graduated cylinder and get a reading for it. But for a gas, it's not fixed. Gases are the only ones that can be compressed. If you think about like a compressed can of like a aerosol spray of any type, hairspray or room fresheners, anything that comes in a highly compressed container. So those are our gases. You can compress a gas. It's the only one that can be compressed. All right, gas molecules always moving in straight line paths at very high speeds. And they only change direction when they collide with each other or the walls. And then the collisions is what produce the gas pressures. And I think if you did the ChemThink, you would have seen this happening with the little particles bouncing around inside of the containers on the ChemThink. All right, so the volume of a gas sample can easily change if an external pressure is applied to it. That's the whole gases can be compressed. So if you know what a syringe is, and so you can push down on a syringe, on like the plunger on the syringe, you can apply a pressure to it and assume this is capped off. So you're not just pushing the air straight out of the bottom. So if there's a cap on here, you can push down and you would have to apply a little bit more pressure, but you could keep pushing that plunger down into the syringe. And so the more pressure you apply to the syringe, the smaller the volume of the gas becomes. So you can see like this line right here. So you're decreasing the volume, but you're increasing the pressure inside the syringe. And so because the particles are colliding with each other and the walls more frequently, that's what results in the increase in pressure. That's what it looks like on a graph. And I do want you to know what these look like graphically. And that shows us that's the inversely proportional relationship. So that's where if the one goes up, the other goes down. So that's pressure over volume. So that type of a shape is the inversely proportional. One goes up, the other goes down. So this is known as Boyle's law. So the law that represents the relationship between pressure and volume and shows how they're inversely proportional is known as Boyle's law. We also see that as an equation. P1V1 equals P2V2. The P1 is initial pressure, V1 is initial volume, P2 is final pressure, and V2 is final volume. The catch here, P1 and P2, they just must have the same units. So it doesn't have to be pascals, but they would both need to be pascals, or they both need to be PSIs, or they both need to be millimeters of mercury. You can't have one be like millimeters of mercury and one be torrs. So you might have to convert one of them to match the other. And then same with your volumes. Your volumes just have to have the same units. So they just have to match. Here's a sample problem. I'm just going to fly through it real quick. If you were to read through this problem, a balloon has a volume of 4,200 liters at 1 atmosphere. Placed in a chamber and decreases the pressure to 0.72 atmospheres. What will be the final volume? So we know the initial pressure and the initial volume. We know the final pressure. We're solving for the final volume. The units here match, atmospheres, atmospheres, and so liters is here, so then our answer is going to be in liters. Plug it into the equation, solve it out, and ultimately you should get 5,833 liters. All right. Then temperature volume. So the law that shows the relationship between volume and temperature, and these are going to be directly proportional. This is Charles's law. So this is as volume increases, temperature increases. If temperature decreases, volume decreases. So here's the equation. Now we're V1 over T1 equals V2 over T2. So we've got our initial volume and our initial temperature, and then we've got final volume and final temperature. The two volumes must be in the same units. The two temperatures must be in kelvins. So temperatures are the ones that you might have to do converting. Has to be in kelvins because we don't want those to get into the negative numbers with the Celsius, or we don't want it to be 0 if it was like 0 Celsius, because then your answer is just going to be 0 no matter what. So if we use the Kelvin scale, we're never going to hit 0 Kelvin or get into any negative numbers. Graphically, this is what a direct relationship looks like. So if one goes up, the other goes up. So the shape indicates that the gas temperature is directly proportional to volume. Here's a quick practice problem. If we make a table listing everything out, it says it's got an initial volume, it's got a temperature that goes from 20 to negative 60. What will the final volume be? So we're starting at 4,200. Starting at 20 degrees Celsius. We don't know the final volume, and it ends up at negative 60. First thing we need to do is get it out of Celsius. So you're just going to add 273 to both of those temperatures, and then plug it into the equation. You can cross multiply. 3,053 liters would be your answer. So then the relationship between pressure and temperature, and it's another directly proportional, is Gay-Lussac's law. So if temperature increases, pressure increases. If temperature decreases, pressure decreases. Here's the equation. P1 over T1 equals P2 over T2. We've got our initial pressure, initial temperature, final pressure, final temperature. Again, it's mostly units must match. The only exception is temperature must be in kelvins. So again, so we don't get into negative numbers or we can't hit 0. Graphically, that's what it looks like. It's another direct relationship. So temperature is directly proportional to pressure. Here is a sample problem. So 2.5 atmospheres filled at 20 degrees Celsius. What would be the pressure inside the container if it were thrown into a fire at 600? So listing that all out. Need to convert to kelvins. So get rid of your Celsius temperatures. Plug it in. Solve at 7.45 atmospheres. And I'll finish up in another video.